Now that we've learned how to find the derivative of pretty much any type of function, let's jump back and do some of the applications that we skipped earlier. In section 3.6, we learn about two of the most common types of applications that you'll see outside of a calculus class. The first being in science classes, working with velocity and acceleration. And the second, just slightly below that you can't see right now, is about what's called marginal costs from a business or economics sort of standpoint. So I guess starting with the position, velocity, and acceleration functions, there's certainly relationships between the three using derivatives because outside of position, velocity and acceleration are just rates of change. Right? So first of all, the position function is really nothing more than a distance function. It's the distance a moving object has moved away from some reference point. It's usually the starting point, but it could just be any point that it passes through at any point during its movement. Okay, so that just gives you the actual position where something's located. The velocity function is the rate of change of the position function. So keep in mind, rate of change is the same thing as slope. And in this context, our slopes are our derivatives. So the fact that we're saying that the velocity is the rate of change is really telling us that the velocity function is the derivative of the position function. Okay, so if you're taking the derivative or the slope of the position function, the label on that's going to be whatever the distance label is from your position function, along with a unit of time. So we're talking about miles per hour, feet per second, meters per second, any of those examples. And you should recognize that as simply just speed from algebra class. But velocity is a little bit different. Velocity is different from speed. Speed doesn't care whether you're going frontwards, backwards, sideways, wherever. Speed is just how quickly the object's moving. Velocity also gives you the direction that that object is moving. Okay, so if the velocity is positive, that means the rate of change of the distance is positive. So the distance is growing, right? Positive rate of change means things are increasing. If the distance is growing, that the object has to be moving away from the reference point so that the distance is increasing. And in contrast, if the velocity is negative, that means the distance is decreasing so that the object must be moving closer to the reference point. Right? Then the acceleration is more or less the same idea. It's just the acceleration is the rate of change of its velocity. So once again, that tells us that the acceleration function is the derivative of the velocity. This one's a little bit harder to visualize, but from experience, we should be aware that if the acceleration is positive, that really means that the object is speeding up. Its velocity is increasing. If the acceleration is negative, then it's excuse me, it's slowing down. Right, so putting it all together, this is really what you need to know about the position, velocity, and acceleration functions for these applications. And typically, you're given the position function and then maybe ask some information about its velocity and acceleration. If that's what's happening, you're working with the first derivative being the velocity and the second derivative being the acceleration. So remember, the acceleration is the derivative of the velocity. If you take the derivative of the first derivative, you get the second derivative. But occasionally you won't be given a position function. Maybe you're just initially working with a velocity function. So in that sort of context, the derivative of the velocity function absolutely gives you the acceleration. Okay, that's it. That's all you need to know from section 3.6 regarding velocity and acceleration. The tricky part, of course, is actually taking these derivatives and using all of the different rules that we've learned and being careful more than anything else that we don't skip any of the steps. Right, so that's one main idea. The other main idea, before we get into some examples, is, as I mentioned, something called marginal cost. We'll actually go ahead and talk about the average cost per unit as well, but these are both ideas from economics or business models. And so in general, if you're trying to produce some sort of product that you're selling, everybody has some sort of cost function. Obviously, it's not usually going to be some sort of math equation that's easy to write down. You're usually using computers to come up with this model. But this is how companies make decisions in terms of how many they should produce, what the price is, those sorts of things. So we're just going to assume at the beginning that the cost function is given to us. And the cost function is always giving you the total cost, not the cost per item, but the total cost of producing X units. So the cost function takes the number of units that you're trying to produce, and it gives you the cost of doing that. Okay, it's the average cost function that gives you the price or the cost per unit when those X units are produced. And so bear in mind the cost functions are usually going to fluctuate. Things are more expensive at the beginning when you're ramping up, buying equipment, those sorts of things. So the actual cost of the units, if you produce 10 of them, is going to be quite a bit higher than the average cost if you're finding the average cost of, say, 10,000 units. Okay, but this again, the average cost function is just the average cost per unit when X units are produced. And the notation there is just a bar above the cost function. And then the marginal cost function gives you an approximate cost of producing one additional unit. Okay, so again, this is an estimate. It's not exact, and we'll talk about it in a little bit more detail down below. But the notation here is not, tricky. It's basically telling you verbatim using the notation that the marginal cost is nothing more than the derivative of the original cost function. Okay, so if you take the derivative cost function, it's going to give you the approximate cost of producing one additional unit after X units have already been produced. Okay, so talking through that just a little bit more, maybe I can squeeze in some typing and then delete it because this isn't hugely important, but I think it's important that you see it for a split second. So just kind of keep in mind here that, as we know, the derivative is nothing more than the slope. Okay, but slope is of course a fraction here. So this is going to be the change in cost divided by, excuse me, the change in the number of units that you're producing. But kind of keep in mind here, we can think about this without any extra information. And this is absolutely kind of the idea going on, but to make this line up all the way across here so that we can see how the fractions interact, you would take your whole number and write it as a fraction over 1. Okay, so here, if we do it that way, and just take the derivative and put it over 1, take the slope and put it over 1, then the numerator of the slope, or the numerator of the marginal cost, excuse me, gives you the change in cost, and that is for exactly 1 unit. Okay, so again, this is an estimate because when we're talking about the derivative, that's instantaneous rate of change. That derivative is not good for one whole unit. It's there for just a split second. But that's the idea of why this is able to approximate or estimate the cost of having that one additional unit. If I had one extra unit, that's going to give me the change in the cost based on the definition of the derivative there. So I need to delete that so that my notes aren't all messed up later on, but that's why it works. Right, so putting it in perspective here then, or I shouldn't say putting in perspective, just an overall summary, you're never going to be asked to find the cost function in this class at least, but given the cost function, be aware that the average cost function is really just that cost function divided by the number of units that you're producing. Okay, and so just keep in mind when you find the average, you add up all the values and then divide it by how many there are. Well, the cost function is just adding up the cost of all of those, to produce all those units, and then we're dividing by the number of units. And so that's why that formula comes to be, but it's really just the cost function divided by X. We already talked about this up above with the notation. I just wanted to make it as clear as possible. That C prime notation for the marginal cost, that's not a trick question or anything like that. That's just what everybody uses. That is still the derivative. So the marginal cost is found by taking the derivative of the cost function. If you wanted to find the exact cost, so I mentioned this up above, I didn't bother to talk about it because I think it's clear what the exact cost means. But if you're looking to find the exact cost of producing one more item, you would actually have to subtract 2 cost functions. And so I know it sounds a little bit weird to have to go through all of this work to find the cost of 1 unit, but that's not really something that's important in business decisions. You're not figuring out, well, hey, what's the cost of this extra unit, and then what's the cost of another unit after that, so on and so forth. You want kind of big picture ideas. And so that's why this is more complicated to get it broken down into the exact cost of one item. But all we're saying to find that exact cost is to take the cost function, evaluate it at 1 more than what you started with. And if you subtract those 2 cost functions, that'll automatically give you the difference in price between that one extra unit versus what we had before. And so you can just evaluate the cost function at one more unit, subtract away the original cost function, that will give you the exact cost. Okay, so just a quick heads up. I would absolutely expect you to memorize the position, velocity, and acceleration information. That's something our textbook will keep coming back to, and it's something that is pretty widespread in a lot of the engineering science courses that a lot of you are going to end up taking after this class. I'm not so worried about you memorizing the ideas of all the cost information here, but I think it is pretty handy to know that you can take the derivative cost function to get an estimate of just how much more it's going to cost to produce an additional unit. But this information maybe not quite as common to run into, but if you're taking this class and excuse me, knowing that you're going to be taking some other business classes, you might as well get used to this notation as well. All right, so let's do a handful of applications. And the first one, actually the first couple, we're going to be talking about, again, the acceleration, velocity, and such. All right, so the setup here is that we've got a weight hanging by a spring, and its height above the floor is measured. Okay, so we haven't moved it yet. It's resting right there on the spring, and so that's going to be our reference point. I pull that weight downwards 3 inches and let go, and of course it's going to start bouncing up and down, up and down, up and down. Okay, so there's a handful of problems like this in, excuse me, in your textbook. There we go. But our textbook, because it's a little bit nicer than I'm going to be, at least in this problem, it gives you some functions here that are based on trigonometry, because trigonometry is what you use anytime you're worried about something oscillating, repeating itself over and over. I put a little bit more complicated of a function here because I want it to be a little bit more realistic. Right? Excuse me, the functions that the textbook use are really, whittled down basic ideas where it's not taking into account the actual action of the spring. Right? If you let go of that spring and watch it bounce up and down, it's going to slowly stop bouncing up and down. It's not going to keep bouncing up and down those 3 inches forever. And so that's kind of the idea of why we have this extra stuff that our textbook usually doesn't put in here. I also have to preface that this is not usually how it would be done in a physics class. You would have some crazy representation, oftentimes using e raised to negative exponents and more complicated fractions. But at least with this function, we get the idea that things are changing. I'm going to switch to a different screen here just so you can see what I'm talking about. If I show you the graph, you can see here, there's the position of the weight before I've let go. It's at -3 because it's down below the resting point when I pull it down those 3 inches. And then it bounces up and then bounces down, bounces up, bounces down, so on and so forth. And you can see, every time it goes up and comes back down, it loses a little bit of its energy, which makes sense. It's not going to keep bouncing up and down at -3 and +3. And along with that, the shallower the bouncers get, the faster it's going to start to go. That's a little bit harder to see here, but I can zoom out. Don't ignore the negative area because that's not part of our focus. You can see here, it's just going to keep bouncing, bouncing, and getting smaller and smaller and faster together until it completely stops oscillating eventually. But it would take a while, but it gets really close together, and I'm not going to show anymore because this is not a perfect, physics representation, but it gives you the basic idea of why I wanted to do something a little bit different than what the textbook did. It's a lot more realistic than just having a normal sine function or cosine function that never fluctuates. So let's go back to the problem itself and recognize then that we're just asked two things. Find the velocity of the weight 1.5 seconds after you let go of the spring, and then find the acceleration 4.75 seconds. And so I don't know that these two numbers are terribly important. They're just something to evaluate. At the end of the day, this is all this is asking is to find the velocity. We need to take the derivative of this function and then evaluate it at 1.5. Once we've done that and we have the velocity function to find the acceleration, we're just taking the derivative of the acceleration function and evaluating it 4.75. That's it. Okay, so that's one of these things that's easier than said than done. It's not a huge new idea, but you can see here that taking the derivative of something that looks like this is a little bit involved. We definitely have the quotient rule going on because we have a fraction with the variable in both the numerator and the denominator. Within that quotient rule, when we go to take the derivative of the numerator, we're going to end up having to use the chain rule because there's some stuff inside of the cosine function. And so, kind of the other idea here, I guess, is along with giving you something more realistic, I wanted to give you a problem that really puts together everything that we've done outside of maybe implicit differentiation with our derivatives and make sure that we have as much extra practice with that as we can, because that is still the main focus of what's going on in chapter 3. All right, so take a look at the solution here. Just drag this down so we can see it. So we are actually already talked about this, that we're going to use the quotient rule to find the derivative, making sure we use the chain rule as we find the derivative of the numerator. Okay, so writing this out step by step just to make sure that we don't lose any information along the way. I don't know why it keeps doing that. But the quotient rule is nothing more. I can scroll up a little bit so you can see what I've done. The quotient rule is right here. Just a heads up, I went ahead and took that 9 out of the fraction, put it in front with a negative sign, just so it wasn't so much to do in terms of the derivatives later on. But the quotient rule is nothing more than the derivative of the numerator multiplied by the denominator minus the derivative of the denominator times the numerator. And then we in the denominator, we have the original denominator squared. Okay, so that's just writing out exactly what we're doing. And at this point, it's just being careful taking the derivative using the chain rule. Derivative over here, not a big deal. Derivative t plus 3 is just 1. But in the first derivative, we're going to have to do a little bit of work with our chain rule. Okay, so again, just kind of working through this. The derivative cosine is negative sign. Don't touch anything on the inside. And then once you get to past that, we have to multiply by the derivative of the inside. Okay, so keep in mind, I kind of tried to write this out to follow along as well. That pi over 2, that is just a constant coefficient, so it's just going to stay put. And then we're taking the derivative of t plus 2 squared. So you multiply by the exponent, decrease the exponent by 1, and I guess technically after that, you're still multiplying by the derivative of the inside, but the derivative of the inside there would just be 1. Okay, so that's the main piece of work here, is using the chain rule to get from the cosine to its derivative with all of this, with the negative sign and such. And again, the derivative of t plus 3 is just 1. Okay, so after that, it's just a matter of keeping track of exactly what's happening. So here the 2's cancel out, so we're just left with a pi. There's a t plus 2 and a t plus 3 that we're multiplying there. So all of this stuff right here just becomes pi times t plus 2 times t plus 3, along with our sine function out front. And notice this isn't the distributive property. This is all multiplication. The only reason the brackets are here is to keep things separated, so it's a little bit easier to see the steps. And on the other side, all I did was say, well, 1 times anything is just itself. Okay, so that's what we get when we take the derivative. And what else? Oh, I guess the last step that I did here, this is completely optional, but it's something that I kind of just naturally do, is notice that both the terms in the numerator here are negative. That would drive me crazy trying to make sure I kept track of the negatives as I type it in the calculator. So all I did in this last step is I factored out the negative from the numerator so that now it's all positive. Factoring out the negative gives you an extra negative sign out front, so the 2 negatives turn into a positive 9 out there. Okay, so finally, all we have left is to evaluate at excuse me, at 1.5. And if you put in 1.5, you'll get a 3.5 in the trig functions that need to be squared. 1.5 plus 2 is 3.5, 1.5 plus 3 is 4.5. So I'm not going to show this in a calculator by any means, but that's just ends up being a calculator problem. Do make sure that your calculator's in radians. Remember that in a calculus class, in general, unless you're told otherwise, you do need to be working in radians. And you throw that in there, you're going to end up with 8.83. And then finally, we just have to answer the question. We know that that is the velocity. We just have to make sure that we put our correct label on here. So I guess I need to go clear back up to the beginning to make sure it's clear why this is inches per second. First of all, it has to be something in this format because it's the velocity, but all we're doing is going back to the original problem and seeing, excuse me, that h of t is measured in inches and t is measured in seconds, so our label has to be in inches per second. Okay, so that finishes the first part of the problem. The second part of the problem, you can kind of see here, it's going to get crazy. And we're supposed to be taking the derivative of the velocity function to get the acceleration function. That is a lot more complicated than any example that we've done previously. And just to talk through it one more time, we'll do it in detail on the next page, but we still have the quotient rule going on with variables both in the numerator and the denominator. This time in the numerator, not only do we have the chain rule that we're going to have to deal with a couple of times here, we also have a product rule going on because we're multiplying a bunch of things with the variable in it as well. And so this is going to get a little bit long. It's not new. There's no new techniques that we haven't done before that we're going to see. It's just going to take a lot more typing. I guess I need to zoom out a little bit. It's going to take a little bit more typing / organization to work through this. And so here's our velocity function from the previous page. And as before, just kind of drag this down and hopefully that little circle doesn't get too much in your way. But the first thing I'm doing is just breaking it down using the quotient rule again. So the coefficient 9 stays up front, and then it's the derivative of the numerator here. So it's the derivative of that whole numerator times the denominator minus the derivative of the denominator is now t plus 3 squared, but we have to take the derivative of that denominator and multiply it times the whole numerator, and then we still have to square the denominator. So squaring the denominator is the easy part. We're not actually going to expand all that out, but use your exponent rules here. When you have an exponent on another exponent, you'll just get t plus 3 to the 4th power. So the denominator is the easy part. The numerator is where all the work is going to come into play. So we're going to split this into the two different individual derivatives. The first derivative that's listed here is the complicated one. This one, I just wanted to make sure that we're clear. We're doing that at the same time here, but just kind of keeping it separate. So just looking at the easier one, sorry, this is just something that we know how to do automatically. This is the power rule, multiply by the exponent, decrease the exponent by 1. And then it's technically the chain rule because we have a function that is being squared, but the derivative of t plus 3 is just 1. So you don't really actually do anything in terms of that part of the chain rule, but you're left with 2 times t plus 3. You can write that as 2t plus 6 if you want, but there's no reason to multiply that out. And over here, we're looking at the derivative of the numerator again. And kind of keep in mind, I'm being maybe a little bit overbearing with the different rules here, but I just want to make sure that we're taking this step by step and seeing how all this would end up being done. But with derivatives, I've said this before, but with derivatives, you kind of want to work from outside in, right? That we're taking the derivative of the whole expression. You cannot separate that into the derivative of the two different pieces here without knowing that you're allowed to do that with the sum rule. So the derivative of sum is just the same thing as the derivative of each individual term. These are huge terms, but they are terms nonetheless here. So the sum rule just allows you to break this down into 2 separate derivatives. And then after that, we're going to break this first one down using the product rule. So notice here the second part of the derivative over here, I just copied down for now so that we're not doing 2 rules at once. And then here, notice that there are 3 different things containing variables that we're multiplying, and we have a constant coefficient. And so when I'm using the extended product rule here, that constant coefficient is just going to stay put. That's why there's a pi just out here by itself. And then there's other ways of doing this, but the extended product rule just tells you can take this one step at a time and take the derivative of the first function and multiply it by the other 2, then add on the derivative of the second function and multiply by the other 2 functions, and take the derivative and then add on, the derivative of that last function and multiply by the other 2 functions. And so that's your giant extended chain rule here. And again, that pi does apply to everything that's in a set of parentheses here. I just didn't want to have to keep writing the pi over and over and over. I was going to end up running out of screen. Okay, so in the next step, we've broken this down far enough that now we can look at this and take the 4 individual derivatives. We'll have the chain rule for this derivative. Here, that's just a straightforward derivative, but then chain rule again. Right. So we saw the chain rule earlier, so this should look familiar. It's just this time we're starting with sine, so the derivative of sine is cosine. Keep everything that was in the parentheses the same. When you take the derivative of the inside, you're going to get that pi over 2 as a constant coefficient. You take the derivative of t plus 2 squared, you're still going to get the same 2 times t plus 2 that we had earlier. Okay, so you're just dropping down the t plus 2 and the t plus 3 from up above. Then the derivative of t plus 2 is 1, so it just disappears. You're left with the sine function times t plus 3. The derivative of t plus 3 is once again 1, so it just disappears. You're left with the sine function and the t plus 2. And then this is actually just a little copy and paste. This is the exact same derivative we started with in the when we were taking the derivative of position function. So this and what we have over here are almost identical. The only difference is when we take the derivative of cosine, we get negative sine, whereas over here, when we take the derivative of sine, we get cosine. Okay. And then finally, it's just keep track of what's happening. So when I say simplify, all I meant was we're canceling out the 2's here in a couple places and then distributing the pi symbol. So keep in mind that we're taking cosine of all of this. So pi is not going into what we're taking cosine of, but it gets multiplied to the stuff that's on the outside. So here, pi times pi gives you pi squared. The 2's canceled out, and then you have a t plus 2 and a t plus 2 is a t plus 2 squared, along with the t plus 3, and then multiply by pi to get, excuse me, the sine of all of this times pi. I squeeze it in there in the middle, so it's right next to t plus 3, and then multiply the last one by pi, and you get the same idea. Just squeeze the pi in there so that's there. And then when we simplify and cancel out the 2's here, notice that at least one nice thing happens. These last two pieces that we wrote down are like terms, and so they just completely disappear. Right? They're exactly the same. One's positive, one's negative. So these guys absolutely just cancel out, and we're left with the end result here. Okay, so that, again, it's a lot of work. It's not something that I would expect you to do on a test or quiz, certainly, and even in a homework assignment. There's no way this is going to come up as something that's complicated. But at the same time, realize that applications are complicated. The further you go on into engineering or economics or whatever it is that you're going to be doing with your calculus uh, knowledge, it's not going to be nice, straightforward equations that you're working with. You're using actual physical equations from real life. They are going to be complicated like this. So I think it's really good for you to see that even if it's an annoying problem and hard to do, we can certainly do it. And so the last thing, I kind of got sidetracked there because we finally got done with all the derivative stuff, but that was just the derivative of this first part. We still have to plug all that back into this original quotient rule fraction. So that is what it would look like. I guess I can go ahead and delete that box now, get it out of the way. You can see the answer, but that's the derivative we just found as the first part of the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator all over the denominator to the fourth power, as I mentioned earlier. Okay, so again, I'm certainly not going to show typing all of this in. Be extremely careful as you put in the 4.75 that you hit all the notation and operations, all of that. I will say I more than triple check this. I probably put this in my calculator 5 times and checked it with Mathematica Online, stuff like that, just to verify that I had the right answer here. But when you plug this in, if you do it appropriately, you should end up with an acceleration of negative 405, more or less negative 405 inches per second squared. Okay, so this is something we haven't talked about. So this is the last quick idea to worry about here. Keep in mind that when we're talking about acceleration, what we're really doing here is talking, I guess I messed that up, but we'll go down, I guess. But when we're talking about acceleration, we're talking about the change in velocity. So again, derivatives are rates of changes, so we're just looking at slope. This is a change in velocity over the change in time. And I only write this out because I want to make sure that you're clear about where that second squared comes from. Velocity is measured in this problem, at least in inches per second. So basically, this is change in inches per second. And down below, a change in time is just nothing more than change in the number of seconds. Okay, so if you're looking at that then, what we're doing is, sorry, dividing inches per second by the number of seconds. And this is nothing more than multiplying that by the reciprocal. Okay, so I'm not going to write that last step since it's already up here, but this is why you get inches per second squared, because you get the seconds twice in the denominator here. So that doesn't have any easy real life meaning, so I'm not going to try to interpret it beyond that. But the further you get in Science C type classes, well, I just messed everything up. I'm glad that we're done with all that up above. But the further you go, the more you realize that labels are there just to make sense out of everything that's going on. This is not there because it's an easy way of describing what's actually happening. It's there because that's what happened when we measured all of this change. We had labels that were input that had inches in it and seconds in it. And when we did all of the different operations, it spit out in inches per second squared. Okay, but anyway, let's stop talking through that because that's just extra information that didn't really have anything to do with what we've been doing in calculus. So that is the acceleration that we are looking for. Okay, so I started with what I would call kind of a hardcore example, just to get you used to the fact that there are some times where you're going to end up needing to do a lot of derivatives and or keep track of a lot of what's going on. The next example I threw in here because we have not actually talked about taking the derivative of a piecewise function. It works probably the same way you would think it would work here, but that's the main idea that I'm throwing out here. So this go around, we're shooting a bottle rocket off the ground on a calm day with no wind. Basically, I'm trying to make this reasonable in terms of why these equations are down here. These still don't account for drag or anything else of that matter, but I went through and made sure that these make sense in the end of the day in terms of gravity, and it doesn't work if you've got extra wind pushing things around. So we're just going to assume that there's no wind, there's no effect of air whatsoever. The rocket burns for an unknown amount of seconds that we'll find later on in the problem. And then after it stops burning, of course, it's going to stop rising and falling back to the ground. The reason that this is actually a piecewise function is because basically you have a portion of the, I guess, the flight, if you want to call it that, where the rockets are, or its rocket is in play and it's being boosted upwards. And then it's not like the rocket just kind of, peters out. It just kind of stops. Maybe there's an instant where it kind of, works its way down. But in these types of rockets, it burns the fuel, it burns the fuel, it burns the fuel, and then all of a sudden it's out of fuel. Okay, so that's why we have a piecewise function. This is where the rocket has fuel and it's going upwards. At this moment, where it runs out of fuel, it's going to go upwards a little bit more because of momentum, but there's no more rocket fuel. And so we have a completely different set of equations to describe what's going on with that. Okay, so that's why we have a piecewise function. But beyond that, it's just asking, hey, find the velocity function, find the acceleration functions. We're just going to take derivatives again of some things that are much easier to work with. And then we'll work through the rest of this in terms of trying to figure out what the value of B is, and then how fast the rocket is moving when it hits the ground. And again, I guess I didn't say this, I'm letting G represent when it hits the ground. And I know this is a little bit weird. I didn't want to give numbers here because I wanted us to go through together and figure out what these numbers have to be based on certain characteristics. Normally it would tell you for, say, the first second, it's the rocket's ignited, and then after that, it's not, and then it hits the ground after, say, 7 seconds, and that's that. Okay, but we're going to have to find the B and the G here as part of the process. That's why they're variables. All right, so the first part's the easier part. The only thing that you need to know is, I mentioned earlier that this works exactly the way that you would hope. The only thing you need to know about working with piecewise functions is when you take the derivative, you're just going to be taking the derivatives of each individual piece. We're not trying to take the derivative of anything over here because this isn't part of the function. This is telling you that this function is good for when the time is less than b. The second function is what we're working with if the time is bigger than b and before you hit the ground. Okay, so this is just kind of telling you which one to use. That's not part of what we're taking the derivative of. We're just taking the derivative of the polynomials over here, right? And so when we take the derivative then, it's not any sort of big deal. We're taking the derivative of each component. Everybody, I'm pretty sure, is comfortable taking derivatives of polynomials. Just make sure that you don't go too fast. Use a calculator because some of these numbers get to be a little bit large here. But that's it. We're just taking the derivative by multiplying by the exponent, decreasing it by 1, term by term. Okay? And then once you have the velocity function, we're taking the derivative of the velocity function to find the acceleration function. So, excuse me, here's the derivative of the velocity function. And once again, just term by term, use the power rule like you have in the past with, excuse me, taking derivatives. Right. So again, it looked a little bit different than what you've seen, but it uses the exact same rules. Okay. And so from here, we really need to figure out what B is before we figure out what G is. Okay, so I'm going to kind of talk a little bit ahead here, but if you're talking about G being when it hits the ground when the height is 0, but we have to make sure that the height is 0 after this B number of seconds. And because its height is 0 at t equals 0, but we don't care about that because 0 is not part of the domain that we're looking at here. And so that's really what part C is about, is making sure that we can figure out what B is so that we can determine what is the actual valid time where the rocket hit the ground. Okay, so the hint that I gave you up above here is copied down below, that based on the nature of movement, as long as it's not hitting a wall or anything like that, it's just moving relatively smoothly, not being knocked out of place, it is going to be continuous. Even if it wasn't moving smoothly, it would still be continuous. It would just be a lot more complicated of a function here. So that makes sense, hopefully, that a moving object here is not just going to teleport from one location to another. It's not like we're doing the X-Men or anything like that. And same thing with velocity. Nothing can go from, in physical the realm, nothing can be going, maybe 2 miles an hour, then instantaneously be going 50 miles per hour. There's buildup in between. Okay? Same thing with acceleration. So all we're going to do here then is just remind ourselves, it's been a while, but if you're talking about a piecewise function being continuous, that means that its individual component functions have to be the same at the transition values. Okay, so what that's saying is, when I evaluate this first equation or first expression at B, I better get the exact same value as what I get when I evaluate the second expression at B. And the same thing is true for the velocity and the acceleration functions. So these equations that I'm writing down are nothing more than saying, well, hey, if I plug B in for t, these two expressions have to be the same. These two have to be the same. These two have to be the same. So that's all that's going on here, is that the first expression of the function and the second expression of the function have to be exactly the same when you evaluate at B. Okay, and so we get kind of 3 different sets of equations. If you wanted to, you can kind of write this out as a system of equations. But notice that that first equation, that's going to be pretty tricky to solve. And even if we did, it'll have 3 different solutions that we'd have to go through and figure out which one's the one that actually is valid for us. Same thing with the velocity function. It would not be as bad. We can use the quadratic formula, but we'd still have 2 different values that we would have to decide which one is the actual value that we're looking at. But finally, the acceleration function, that's really straightforward. Right? That's by far the easiest one of these equations to solve. And there is just going to be one answer. So we'll solve this, find the value of B, and then just verify that that same value of B is going to work for the other functions as well. Right, so moving this down further, when you solve the acceleration function, all you're doing is subtracting the 328 from both sides, dividing by the 720, and surprise, I made this work out nicely for you at least, but your value of V is half a second. And so now we're just going back and making sure that everything else makes sense. If you plug in the 1/2 into the velocity function, on the right-hand side, sorry, not the right-hand side, the left-hand side, you plug in the 1/2, you end up with 74. On the left-hand side, you plug in the 1/2, you get 74. That's perfect for us. The 2 values match when we plugged in B equals 1/2, and then check the position function all the way to the top. So plug in the 1/2 to the left-hand side, plug in the 1/2 to the right-hand side. In both cases, you end up with a 26. Okay, so that just verifies that b absolutely needs to be 1/2 in order for all of these functions to be um, the same at that transition value. Okay, so now I'm not going to rewrite it, but now we know that this first function is good from 0 to 1/2. The second function is good from 1/2 up until it hits the ground. Okay, so the last thing that we were asked to do is actually figure out when does it, sorry, not when, but what the velocity is when it hits the ground. In order to do that, we have to start by figuring out when does it hit the ground. Right? We need to find the value of g so that we can plug that into our velocity function and actually come up with the speed that it's moving when it hits the ground. Okay, so one of these we've already talked, well, actually both of them we've talked about, but the two things we know about g is if we put g into the height function, we should get 0 because when it hits the ground, lands, whatever you want to call it, its height above the ground is going to be 0. And then we know that g has to be after that 1/2 a second, right? For the first 1/2 a second, the rocket is being propulsed upwards. So there's no way it could be hitting the ground before 0.5 seconds. Okay, so putting that together, it was clear earlier, but just to restate it, that does mean that we are technically setting the piecewise function equal to 0, but that's the same thing as solving the second expression within that piecewise function set equal to 0. Okay, so here we can't get around this. We do need to use the quadratic formula. So this is, again, negative b plus or minus b squared minus 4ac all over 2a. Just plugging those numbers in appropriately. Use a calculator. You come up with two different answers, of course, because it's a quadratic equation. But this guy is no good, right? We know that the time that it hits the ground has to be after that 1/2 second. So this is the one that we ignore. This must be the amount of time that it takes for it to hit the ground. Now that we know that, there's nothing more than just evaluating the velocity function at 5.45. Okay, so just like I said, we know that we could throw this one out. It has to be 5.45. Now we're just evaluating the velocity function at 5.45. Whoa, that, I have no idea where that crazy number came from. This number down here is correct. So I guess I'll fix that real quick. I must have been copying and pasting from elsewhere and forgot to change a number. But you plug that in and it pops up and tells you the velocity is negative 84.4. And going back and talking about the sign here, it makes sense that this is negative. Remember, velocity measures how quickly it's moving away from the reference point or towards the reference point. Away would be positive because the distance is growing. If you're getting closer and closer to the ground, the distance is decreasing. And so the velocity is negative here. And this time around, this is the first one that we've actually been asked to label, but we were working with the height being measured in feet and t being measured in seconds. That's where we're getting our label from. All right, so last example goes back and we'll talk about the cost function. This goes much faster because there's not nearly as many details that we can kind of mentally keep track of. But all I'm doing is giving you a cost function. This is probably not a very good cost function, but at the same time, it hopefully makes sense. You know, if you put in 0 into our cost function, we're assuming, I guess this isn't necessarily universal, it just depends on your situation, but we're assuming that we were maybe stupid and spent $5,000 on equipment before we even produced one. So if I put in x equals 0, you end up with 5,000 plus natural log of 1. Sorry, 2,000 times the natural log of 1. Natural log of 1 is just 0. So this is kind of our upfront costs. And then after that, keep in mind that the natural log graph is the one that kind of goes up quickly, but then dies down. So as I mentioned earlier, when you're making your first set of producing your first set of units, the cost is a lot higher because you have things that you're having to purchase for the first time as you go along, and it gets lower and lower as it goes forward. Okay, so this at least makes sense as a cost function. I don't know that it's an actual good cost function, but at least makes sense. All right, so here we are assuming that the cost is going to give us a cost in dollars. X is the number of products being produced, so on and so forth. And so just going down the list here, we're looking to find the marginal cost, which, as a reminder, is nothing more than the derivative of the cost function. So when we take the derivative of that cost function, the derivative of a constant is 0. The 2,000 is a constant coefficient, so it just stays. The derivative of natural log is 1 over whatever you're taking the natural log of, and we're multiplying using the chain rule. The derivative of x plus 1 is just 1. Okay, so again, wrote down maybe more than I needed to. If you put all that together, you basically just end up with 2,000 divided by x plus 1. Okay. If you're finding the cost of producing 10,000 units, the rest of these I should have made clear. This is just making sure that you know what to plug in where, what formula you're using. So to find the cost of producing 10,000 units, we're just finding the cost. So just use the cost function. We're plugging that 10,000 into the cost function, and that is going to end up being a calculator problem. But if you plug the 10,000 in, you end up with the logarithm of 10,001 because we have the x plus 1 there. But there's nothing else going on other than making that or putting it in your calculator and rounding correctly. So I'm not going to talk through that in any more detail. In the next one, sorry, I should have read it before I went down there. We're looking for find that average cost. Okay, so remember the average cost was the cost function divided by the number of units that you're producing. So the cost function evaluated at 7,500 obviously gives you the total cost. We divide by 7,500 to get the average price per unit. So again, just evaluate the cost function, get what you get, divide that by 7,500, and you end up with about $3.05 per unit for this particular cost function for the first 7,500 units. Okay, if you're asked to use the marginal cost to estimate the cost of producing the 5,000th unit, here we have to be a little bit careful because it's easy to plug the wrong number in here, right? So the marginal cost tells you how the, excuse me, the marginal cost tells you how the marginal cost tells you the price of one additional unit. So the 5,000th unit is one more unit than the 4,999th unit. So you can kind of have seen that already because I've moved this too quick. But if you're finding the cost of the 5,000th unit, then the 4,999 units have already been produced. This is the extra unit that gives you the 5,000th. So when you're evaluating the marginal cost, it's not evaluated at the unit that we're trying to get to, it's evaluated at one less. Okay, and when you plug this in, again, to the marginal cost up here, you're going to get literally 2,000 divided by 5,000, which is exactly 0.4. Okay, so again, this is an estimate, but the estimate's exactly 0.4 or 40 cents to produce the 5,000th unit. If we're going to compare that using the exact cost to see how good of an estimate we have going on here, the exact cost we mentioned a long time ago now, I've been talking for a while, it's the cost function of the 5,000th unit minus the I said that wrong. It's the cost of producing 5,000 units minus the cost of producing 4,999 units is going to give you the cost of the 5,000th unit. Okay, so we're just plugging that in to our cost function twice and subtracting. This is again a calculator problem, and it breaks down in your calculator as 0.39996 and then some junk after that. But the moral of the story here is that the estimate isn't perfect because this would be the actual cost based on our cost function up above. But of course, this is still going to round to the exact same price here. So this isn't always accurate, right? This is a prediction. Depending on what's going on in the cost function, this might be off by a few cents. But more often than not, especially when you have relatively large numbers that you're putting into your cost function, the marginal cost and the actual cost, when rounded to the nearest penny, end up being pretty much the same thing. Right, so that those are the two main examples from section 3.6. You don't have to worry necessarily about the specific functions that we were using for the cost function or the previous position functions, but the details that we talked through in terms of being careful that we're using the new information with derivatives of logarithms along with our old product and chain rule and stuff like that. That is crucial that you feel comfortable enough with those that you can use them in some of the problems that we're working with here. Right, so that finishes our discussion of section 3.6. I'll be back with the next set of applications in section 3.11.